Hello, class. Welcome to the lecture for it's Wednesday, um, April the 15th. I hope everyone is doing fine. I have, as you probably are aware, I have graded and emailed your test number 2 back to everyone, and the grades in the WebAssign gradebook are um, it should be all up to date, including the calculus flux, which I've also updated. I've had questions about the calculus flux and the attendance policy. So the attendance policy is still in effect for earning flux dollars, right? So if you were, I'm going to count your attendance, your daily attendance before spring break, and then your class participation after spring break, right, since we've been online. So that would be, if you've been doing your homework and, of course, submitting the tests and so forth, then that will is what I'll use to judge your attendance after spring break. And so, again, if you don't violate the attendance policy, then you will still earn the 25 flux dollars, right? And then, you can use that at the end of the semester for um, either maybe buying out of the final exam or buying midterm points, right, as stated in the syllabus. So calculus flux is still working. I know a lot of you have been going to Taylor's SI session, so you've been um, earning flux dollars that way. Our last class day is coming up really pretty quickly, so that's Monday, April the 27th is our last class day, so that's when our third test will be, or that's when I'll post the third test, and then you will, just like this last test, you will return that to me by Wednesday, April the 29th, and then our final exam, I believe, is the following Wednesday. Forgot what day that is in May, but I think the following week is our final exam. So, and so again, that will be posted online, and then you will write your answers and then email those back to me, just like with test number 2. That seemed to go fairly smoothly, so we'll just continue following that procedure. I want to make everyone aware of the of your homework, right? So if you're logging into WebAssign, of course, you're seeing the due dates all the time. So we do have a homework due on Wednesday. That's the one on trig substitution. So that's due the Wednesday, April 15th. So maybe that's when you're watching this video, due at midnight. And then we have another one coming up the following Monday on improper integrals. So we finished talking about improper integrals on Monday's lecture, Monday, April 13th lecture. And also talking about L'Hopital's rule in Monday's lecture, which is due on Wednesday. So we're going to start with a new topic today, which is a little bit different, okay, than any of these topics. So be sure that you're, again, keeping up with your homework, right? That's an important part of your grade, but I'm also using that to get an idea of your class participation to judge your, whether you get those attendance, those 25 attendance calculus flux dollars, right, at the end of the semester. Okay, so that's my announcements. And so let's go ahead and jump right into the notes here. So let me switch to the notes, and we're going to take up this new topic today, which is about series. And series is a kind of a generalization of the notion of definite integration. All right, and so what we're doing now is related to definite integration, but not quite the same thing, right? So remember that when we were talking about definite integrals in the context of computing volumes, remember we really sort of dug deeply into the meaning of what a definite integral is, right? So we could apply that to computing volumes of you know, solids of revolution, right? And so remember, we gave this formal definition, right, of a definite integral. And so remember, definite integral was a limit of a sum that had a lot of terms in it, right? Okay, and so the definite integral was the limit as the number of terms in this sum went to infinity. Remember, the parts of this sum we defined, right? This delta x was, remember, it was the difference between the upper and lower bounds of your definite integral divided by n, the number of terms in the sum. And then this value, x sub I star, right, was chosen in this interval, right, between the lower bound and the upper bound of the definite integral, correct? So my point is here is to not revisit this definition of definite integral, but just to remind you that in a sense, a definite integral can be regarded as a sum with infinitely many terms in it, infinitely many quantities that are added together. Because remember, in this sum, we're going to take the limit as the number of terms in the sum, the number of quantities that we're adding together in the sum, is going toward infinity. So in a sense, a definite integral is an infinite sum. It's a sum of infinitely many quantities, right? Okay, and so that's the idea that we're going to start from today, and we're going to generalize this idea. Okay, so whenever we have a sum, it doesn't have to come from a definite integral. It could, but it doesn't have to come from a definite integral. But whenever we have a sum that has infinitely many terms in it, infinitely many things that we're adding together, we're going to call that sum a series. All right, so a series is a sum with lots of quantities that are added together. All right, and but with infinitely many of them. All right. So that's a series. So here's an example of a series where you're adding together a lot of terms, right? I don't have you know, specific values for the terms, so I'm just labeling them with the variable a and these subscripts here. So a sub 1 is a quantity, a sub 2 is a quantity, a sub 3 is a quantity, etc., etc. But we've got infinitely many of these quantities, these terms that we're adding together. So again, that's called a series. And what we're going to explore here in this notes, in this section, is some of the sort of basic properties of series. When you look at a series, an infinite sum, the first thing that your intuition tells you is, oh, the sum of that series is going to be infinite, right? Because there are infinitely many terms, infinitely many quantities that I'm added together. But remember, this is calculus, right? And often in calculus, right, we realize that some things that we think are going to result in infinity actually don't result in infinity, and that's what's going to happen in series as well. All right, now it gets a little bit tedious when you're writing down a series to write out all of the terms in the series, you know, just one by one, you know, the first term plus the second term plus the third term. So we often use this shorthand notation to represent a series. So this is called summation notation or series notation. And so we use this this Greek letter capital sigma. That's the Greek letter capital sigma. And so that's sigma for sum. And then we usually put a subscript on each one of the terms, right, of our series, right? And so what this notation means is just like it did for with a definite integral, right? This means we're going to first let n be 1, and then we're going to let n be 2, and then we're going to let n be 3, all the way up to, see, n can go all the way up to infinity, right? And so we're adding together here, the sigma means adding. So we're adding together a1, right? Because when n is 1, you get a sub 1, and then when n is 2, you get a sub 2, right? When n is 3, you get a sub 3. So this is just a shorthand notation, right, for this big sum, okay? And so we often use this summation notation or this series notation to help us express a sum, because it gets difficult to write out all the terms of a sum. You'll see this very clearly when we look at some specific, this is kind of abstract, but when we look at some specific examples of a series, then you'll see why this notation is helpful. All right. By the way, this subscript here that we put on each of the terms, that's called the index of the term. All right, so a sub 1, 1 is the index, a sub 2, 2 is the index, a sub 3, 3 is the index, and so on and so forth. All right, now, in practical terms, of course, you cannot physically add infinitely many things, right? You cannot compute the sum of infinitely many things, right? Because you don't have time to add infinitely many things together. So when we're adding, when we're evaluating a series, right? When we're trying to study series, what we'll often do is stop the sum at some particular index k short of infinity, okay? And so we'll add up the terms of the series up to some given value for the subscript here, for the index k. And so that won't be the entire series, right? Because remember, the entire series has terms where the index goes all the way to infinity. But that will only be part of the series. And this is called, when you stop at a particular index value k, this is called the kth partial sum of the series. And we're frequently in this class going to denote the kth partial sum by s for sum, right? And then sub k, all right? So for example, s sub 1 would be just a1 by itself. S sub 2 would be a1 plus a2. See, you're going to stop adding after the second subscript, right? S sub 3 would be a1 plus a2 plus a3. You're going to stop adding after the third subscript. Up to S sub k, right, would be a1 plus a2 plus, etc., up to plus here, etc., up to a sub k. All right. So when you're armed with the definition of the partial sums, now you can give a definition for what the sum of the entire series is, all right, where you're adding up infinitely many of these terms. So our definition for the sum of a series is going to be the limit as k goes to infinity of the kth partial sum. In other words, if you add up k of these items, you get some value, correct? And then take the limit as k goes to infinity. And it's much easier to analyze the behavior of series by using this definition for the sum of the series, okay? So add up the series to some fixed value k, and then take the limit as k goes to infinity. So this is exactly how we were analyzing definite integrals, right? Okay. Notice it's exactly the same limit that we were analyzing when we were trying to explore the values of definite integrals back there a few sections ago. All right, so sometimes this limit will exist, and if this limit exists, we say the series converges. But sometimes this limit will not exist, and in that case, we say the series diverges. So we're going to be analyzing limits here when we're trying to analyze what the sum of a series is, okay? Again, what makes that difficult is there are infinitely many quantities that you're adding together in the series, so it's hard to figure out what the whole series is going to sum to, right? Okay, when you're adding infinitely many items together. But sometimes it turns out that although you have infinitely many quantities you're adding together, the sum turns out to be not infinite, it turns out to be finite. In that case, we say that the series converges. But sometimes you'll add these infinitely many quantities together and you will get infinity, and in that case we say the series diverges. And this is the big question that we really want to ask about when we're looking at series, okay? Here are the key things. Does the series converge? So does the series converge to a sum? Even though it has infinitely many terms in it, does the series add up to a finite number? And if it does converge, what is the sum? Okay, in other words, what is that limit that the partial sums converge to? Okay, so all of this is going to seem rather abstract, right? Until we look at rather vague, right, and abstract until we look at some specific examples. So that's exactly what we're going to do now. Okay. All right. So let's start with this example 1, which is a very basic series. Okay. This one occurs quite frequently. Right. So notice in this series, what we're adding together here are reciprocals of powers of 2. All right. So there's our series. It's the sum from n equal 1 to infinity of 1 over 2 to the nth power. So let's write out some of the terms of this series so we can get an idea of, you know, what numbers it is that we're adding together, right? Okay, so all you do there is to generate those terms is just start your index at 1 and then let the index count up, right? Okay, ideally all the way up to infinity, but of course we can't go that far, right? Okay, so we'll only write down a few terms of this infinite series. So what happens when n is 1? Well, you get 1 over 2 to the first power. In other words, that's 1/2, right? What happens when n is 2? You get 1 over 2 squared, right? Notice you're adding these numbers together. When n is 3, you get 1 over 2 cubed, right? When n is 4, you would get 1 over 2 to the 4th power. When n is 5, you would get 1 over 2 to the 5th power. And since your index is going to infinity, right, then this sum continues out to infinity. So notice you're adding together in this series infinitely many. These are all positive numbers. So you're adding together infinitely many positive numbers, which would give you the impression, right, that this sum will eventually become infinitely large. But I claim that's actually not the case. Okay, this series actually does sum up, even though it has infinitely many numbers in it. These numbers do add up to a finite value. Okay, I'm going to demonstrate that for you in 2 ways in just a second here. Let's look at some of the partial sums, though. All right, let's look at some of the partial sums. So let's look at the first partial sum. So that's just the first term of the series, which of course is 1 over 2 to the first power, which is 1/2. What about the second partial sum? That would be the first 2 terms of the series. So that's 1 over 2 plus 1 over 2 squared. That's 1/2 plus 1/4. By the way, that adds up to 3/4, right? 1/2 plus 1/4 is 3/4. What about S sub 3? Okay, that's the first 3 terms of the series. So that's 1/2 plus 1/4 plus 1/8, right? Okay. Remember, when you put the capital S with a subscript here, that means just the sum of that many terms, whatever the subscript is, that many terms in the series. So we get 1/2 plus 1/4 plus 1/8. That turns out to be 7/8. I'm not going to do the arithmetic here, but that's what that works out to be. What about S sub 4? The fourth partial sum, that would be 1/2 plus 1/4 plus 1/8 plus 1/16. That adds up to 15/16. So remember, what we call the sum of the series, right? That's going to be the limit as k goes to infinity of these partial sums, right? Do you see a limit here already? Let's see. 1/2, 3/4, 7/8, 15/16. What are these partial sums? What number are these partial sums apparently converging to? That's what we want to find out here. Remember, this is also the same as the limit as k goes to infinity of the sum n equals 1 to k of 1 over 2 to the nth power, right? Okay. See, in the series, your index goes to infinity, but in the partial sum, you're just going to let your index go to some fixed value k, and then to find the sum of the series, you'll think about, what's the limit of those partial sums as k goes to infinity. So as we add more and more terms on here, what are these partial sums converging to? All right, I'm going to show you actually 2 ways that we can figure out what these partial sums eventually converge to. All right. Let me show you here one way. This is kind of a geometric description of why this series actually does converge. So even though it's got infinitely many terms, why there's a finite sum to the infinitely many terms in this series. So here's my geometric argument. Let's look at this square that I've drawn up here, okay? And I've drawn the square so that each side of the square has length 1, all right? So the length here is 1 and the width is also 1, okay, for this square. Now, you know, by the way, that the area of this square is 1, correct? Because that's the area of a square formula from geometry, right? It's length times width, right? So 1 times 1 is 1. But let me show you another way you can compute the area of this square, all right? The total area of this square. Look, let's start by cutting the square in half, right? Okay, so this side, since the total area is 1, right, you know that this piece of the square, right, this shaded piece here that I'm coloring in here, right, that has area, just that piece has area 1/2, right? And then let's take this remaining piece and let's cut it in two. And what is the area then of this shaded piece on top? Well, that's 1/2 of the 1/2 on top, right? So this area, of course, is 1/4. All right, now I'm going to continue doing this. So let's take this piece, this clear 1/4 of the square here, and I'm going to cut that in half. All right, now I'm going to shade this part. So what's the area of this little shaded part? Well, it's 1/2 of this quarter up here, right? 1/2 of this quarter is 1/8, right? Then just keep going. Take this clear part and cut that in two, and now I'm going to shade in this piece, right? What's this piece? Well, that's 1/2 of 1/8, which is 1/16. So notice if you continue this process of, cutting these clear parts in half and then shading in part of them and then adding in their areas, eventually you will shade in the entire square, right? So eventually these fractions will have to add up to the area of the entire square, right? Okay, so if I keep, continuing this process, cut this one in half, shade that in, cut this in half, shade this in, right? Cut this in half, shade this in. Eventually, I'm going to fill up that entire square, right? Eventually, I'm going to have the entire square shaded. And so that tells me then that 1/2 plus 1/4 plus 1/8 plus 1/16, if I keep adding these fractions together indefinitely, in other words, if I keep filling up these halves of these remaining pieces, right, indefinitely, I'll eventually fill up the whole area, and that's an area of 1. So these fractions must eventually, at infinity, right, add up to 1. Oh, so that's neat. So I know that indeed the sum of, but these fractions are exactly this series, correct? Right? This is exactly the same series that I wrote down here. So I know here this series does indeed add up to 1. See, so even though it's got infinitely many terms in it, if you add up all those numbers out to infinity, eventually they add up to 1. That means that this limit, the limit of the partial sums as k goes to infinity, also is 1. Is that what it looks like? These numbers are converging to 1/2, 3/4, 7/8, 15/16. If you keep computing these partial sums, it looks like they're converging to 1. Yeah, kind of, right? Okay. There's certainly already, we can see a pattern here where these partial sums are getting closer to 1, correct? All right, let me show you another way now that we can prove that the limit of these partial sums as k goes to infinity is 1. In other words, the sum of this series turns out to be finite. It turns out to be exactly 1. So this series converges. That's the terminology we use. This series converges because it has a finite sum. All right, so let me show you another way. Other than that geometric argument, let me show you another way that we can demonstrate that this series converges. All right, so I'm going to play a little game here. Here is the kth partial sum, correct? This is the kth partial sum. There was the first partial sum, second partial sum, third partial sum, up to the fourth partial sum. Here's what the kth partial sum would look like. So it's going to be 1/2 plus 1/4 plus 1/8, all the way up to the kth term, which is 1 over 2 to the k power, right? So there's the kth partial sum. Now, what happens, though, if you take 1/2 times the kth partial sum? So I'm going to multiply s sub k times 1/2. Well, the way I do that, of course, is just multiply both sides by 1/2. So I multiply all of these fractions on the right-hand side here, all of them by 1/2. So notice that's going to give me what? 1/4, because you get 1/2 times 1/2 is 1/4. And then 1/2 times 1/4 is 1/8, right? And then 1/2 times 1/8 is 1/16, etc., 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 up to this last term. So that would be what? 1/2 times 1 over 2 to the k power. But 1/2 times 1 over 2 to the k power, that's just 1 over 2 to the k plus 1, correct? See, you multiply 2 times 2 to the k, you get 2 to the k plus 1. Oh, so there's what 1/2 times s sub k is, right? It's 1/4 plus 1/8 plus 1/16, etc., up to 1 over 2 to the k plus 1. You're just multiplying an extra 2, right, into each one of these denominators. All right, now that's the first trick I was going to play, is multiply s sub k, the kth partial sum, by 1/2. Now I'm going to take s sub k and subtract off 1/2 s sub k. So I'm going to take this and subtract off 1/2 s sub k. Of course, what does that give you? Well, if you have s sub k and you subtract off half of an s sub k, you get 1/2 of an s sub k, right? That's like 1x minus 1/2 x is 1/2 x, right? Or 1 apple minus half an apple is half an apple, right? So on the left-hand side, we can see that this difference is going to be 1/2 s sub k. But now look what's happening on the right-hand side. You're taking s sub k minus 1/2 s sub k, right? So let's write that out. We get 1/2 plus 1/4 plus 1/8, right? Plus, etc., etc., plus up to 1 over 2 to the k, and we're subtracting off now 1/2 of s sub k, so that's 1/4 plus 1/8 plus 1/16, right? Plus, etc., up to 1 over 2 to the k plus 1. See that? So you got, there's s sub k, right? And now you're subtracting off, so all of this is s sub k, right? And you're subtracting off this, which is 1/2 of s sub k. Now, what happens when you take these terms and subtract off these terms? Well, notice a bunch of things are going to cancel. You're going to get 1/4 minus 1/4, right? So this 1/4 and this 1/4 are going to go away. You're going to get 1/8 and then a minus 1/8 here, right? Okay. In fact, everything is going to cancel out except the 1/2 and the 1 over 2 to the k plus 1. So all of this reduces quite nicely. All of this reduces quite nicely to, see if I can fit it in here, we just get what? Remember, this is 1/2 s sub k, right? So I have 1/2 s sub k is equal to 1/2, that's left, and then minus, the 16th is gone, but this is left, minus 1 over 2 to the k plus 1. Now, so that's what 1/2 s sub k is, right? Now multiply everything by 2. So I'm going to multiply this by 2, and I'm going to multiply this side by 2. Of course, here the 2 times the 1/2 cancel. So you get s sub k is just equal to, look, 2 times 1/2 is 1, minus, and then when you multiply this 2n, right, into the numerator, it's going to cancel with one of the factors of the 2 in the denominator, so you get 1 over 2 to the k power. That's what s sub k is. There's a simplified version of s sub k. Oh, that's neat. It's 1 minus 1 over 2 to the k, right? So when you add up all these fractions in s sub k, you end up with 1 minus 1 over 2 to the k power. That's the fraction that you get. All right, now, what do we do with that fraction? That allows us to analyze the sum of the series. Because remember, by definition, what's the sum of the series? It's the limit as k goes to infinity of s sub k. So you have the limit here as k goes to infinity of s sub k, but there's s sub k. S sub k is 1 minus 1 over 2 to the k power. And now I think you're really good at analyzing limits like this one, right? What's going to happen to this quantity as k goes to infinity? Well, that means 2 to the k will be a very large number. So you have 1 divided by a very large number. That's essentially 0, correct, right? So you end up here with 1 minus 0, 1 minus 0, which is 1. So again, we get the same answer we got from our geometric argument. When you add up these reciprocals of powers of 2, guess what? They add up to 1. So they converge. You don't get an infinite sum here. You end up getting just actually a small number here, right? The number 1. So here's a series. Even though it's got, again, infinitely many terms in it, we're adding infinitely many quantities. It converges. You get a finite sum. In this case, you get 1. Wow. All right. So see, that is the sort of analysis that we're interested in doing with series. We want to know, again, if I'm just given a series, right, that's an infinite sum, is it going to converge? Or does the sum just turn out to be infinity? In which case we say the sum diverges. All right, well, we got to try another one here, okay? All right, so a little bit harder. All right, I'm going to have to erase here some of the, maybe I don't have to erase them. Let's just move them over a little bit. I have to erase some of this stuff I wrote down. I was going to erase it from the previous problem, but let's just see if I can move that out of the way without really erasing it. So you'll still have it in the notes. Okay. All right. So here is my. Let's block this off so we don't confuse example A and example B. All right. So here's example B. All right. So I'm going to now analyze this series. So it's the sum from n equal 1 to infinity of 1 over n minus 1 over n plus 1. So there's what my terms are going to look like. They're still reciprocals, right? But not quite like in example A. All right, so I'd like to get a feel for how this series works. So what I'm going to do first is write down. I'm going to write down some of the partial sums, okay? And so we can get a feel for what these partial sums are. And remember, and the partial sums are really important, right? Because if the partial sums are converging, then we know the series converges, right? But if the partial sums are not converging, then that means the series is not converging either, right? Okay, all right, so we're going to analyze this series in just a second, but let me pause here for just a moment, all right? And then I'll be just back. Okay, let's look at our next example of a series here. So this is the sum from n equal 1 to infinity, but notice the terms here now are a little bit more complex than in the previous example. The terms are 1 over n minus 1 over n plus 1. And so again, as with all series, we want to determine, does this series converge? So does this infinite series have a finite sum? And if it does, we'd like to find out what that sum is. All right, so again, the key to this is going to be looking at partial sums, right? So I'm going to write out a few of the partial sums just to get a feel here for what the partial sums look like. So the first partial sum, right, that's just the first term of the series. S sub 1 is just going to be the first term of the series. So you just use n equals 1 and plug that into this formula. So you get 1 over 1 minus 1 over 1 plus 1. And so that's what? 1 minus 1 half, which is 1 half. So our first partial sum, same as the first term of our series, is 1 half. What about S sub 2, the second partial sum? So that's going to include the first partial sum, which is what we wrote down here, right? Okay. And then the second term would be when n is 2, 1 over 2 minus 1 over 2 plus 1. So that's 1 half minus 1/3, right? Okay. All right, so let's see, what does that actually turn out to be? Well, notice here that the 1/2s will cancel, right? And so you end up with just 1 minus 1/3, which is 2/3. All right, so the second partial sum is 2/3. What about the third partial sum? Well, let's see, that's the first term, 1 minus 1 half, and then the second term, 1 half minus 1/3. And now when n is 3, you get 1/3 minus 1 over 3 plus 1, right? 1 over 3 minus 1 over 3 plus 1. So that's 1/3 minus 1/4. All right, so let's see what all these terms add up to. So notice again here we get this nice cancellation, right? So we get minus 1 half and plus 1 half. Those two cancel, and then minus 1/3 and plus 1/3. Those two cancel, so you end up here with 1 minus 1/4, which is just 3/4. So I wonder if those partial sums are converging to some number. Maybe they're converging to 1, right? 1 half, 2/3, 3/4. Maybe converging to 1. Let's look at just in general the kth partial sum, okay, S sub k. So that would be the first term, 1 minus 1 half, the second term, 1 half minus 1/3, the third term, we wrote down that was 1/3 minus 1/4, etc., right, up to what's the kth term of this series. So what's this term equal to when n is equal to k? Well, you get 1 over k then, right here, minus 1 over k plus 1. Now, I want you to notice, though, that actually you can compute this partial sum rather easily, right? Because, and we saw the same pattern occur in these first three partial sums. Notice here you have minus 1 half in the first term, but in the second term you have plus 1 half. So those will cancel. And then in the second term you have minus 1/3, but in the third term you have plus 1/3, right? So those are going to cancel. And this same cancellation is going to continue. You're going to have minus 1/4 in the third term, but that's going to show up as plus 1/4 in the next term. So this is going to cancel. And so it turns out that the last term, the last part of each term and then the first part of the next term are going to cancel each other. So that keeps going, and all you're going to get left with here is the 1. It doesn't get canceled, and the minus 1 over k plus 1. So that's what the value of your kth partial sum is. It's 1 minus 1 over k plus 1. But remember, what's the sum of the series? That's the limit as k goes to infinity, right, of your kth partial sum. So that would be the limit as k goes to infinity of 1 minus 1 over k plus 1. And, well, what's that limit as k goes to infinity of 1 minus 1 over k plus 1? Well, as k goes to infinity, k plus 1 is going to infinity, right? So you get 1 over infinity. That's a very small number. So you end up here with just 0, right? I'm sorry, just 1, right? This becomes 0. And all your, as k goes to infinity, the second quantity becomes 0. And so in the limit, you just get 1. So here's another series that converges, and same sum as the prior example. This one also is converging to 1. All right, well, there's two convergent series. Let's look at a series that doesn't converge. Here's a very easy example of a series that does not converge. So, what's the limit as, let's see what happens here, of this sum. The sum is from n equal 1 to infinity of 1. So, what's happening in this series is all the terms are the same. It doesn't matter what the index value is. All the terms are the same. They're always 1. So s sub 1 would just be 1. S sub 2 would be 1 plus 1. The first two terms of the series are both 1. S sub 3 would be 1 plus 1 plus 1, right? Okay. Because again, all the terms of the series are always the same. It's always 1. So s sub 1 is 1. S sub 2 is 2. S sub 3 is 3. In general, for the kth partial sum, you get 1 plus 1 plus 1, etc. up to, well, how many of these 1s are you going to have? It's going to be k of them, right? Okay, in the kth partial sum. So when you add k 1s together, that just gives you k. And what's the limit then as k goes to infinity of the kth partial sum? Well, that would be the limit as k goes to infinity of k, because the kth partial sum is k. But that's kind of an obvious limit, right? As k goes to infinity, that means k is going to infinity, right? So, so in this case, your series diverges, right? These terms do not add up to a finite value. They actually add up to an infinitely large value, right? Okay, so here's an example of a series that diverges. So this series diverges. Does not have a that series does not have a finite sum. All right, here's our last example that's going to be tricky here to analyze, okay? But you're going to like the analysis of this one. All right, so it doesn't look that bad to start with, right? The terms here of this series are 2 over 4n squared minus 1. So we want the sum from n equal 1 to infinity of 2 over 4n squared minus 1. So let's write out some of the partial sums of this series, okay? Because the terms here are a little bit more complicated than in the prior examples, right? Each term 2 over 4n squared minus 1. All right, so let's see, what's s sub 1? So s sub 1 just means the first term of the series. So what do you get when n is equal to 1? Well, if you plug 1 into this formula, you get 2 over 4 times 1 squared minus 1. And that turns out to be 4 minus 1, which is 3, right? So s sub 1 is just 2/3, okay? Now, what about s sub 2? So what about the sum of the first two terms in the series? Okay, well, let's see. The first term of the series was 2/3, right? So we can use that again. And then what about the second term of the series? So what do we get from this formula when we plug 2n for n? Well, when you plug 2n for n, you're going to get 4 times 2 squared. So that's 16 minus 1 is 15. So the second term of the series is 2/15. So S sub 2 would be 2/3 plus 2/15, right? And so 2/3 plus 2/15. So let's see, what's our, I think our common denominator there is 15, right? So we get 10, 2/3 is 10/15 plus 2/15 is 12/15, which reduces to 4/5. So S sub 2 here is, our second partial sum is 4/5. So let's see, does this look like it's converging? Well, don't know just from two partial sums, right? You have 2/3 and then 4/5. Let's see what happens in the third partial sum. So I've written that out for you. Again, you're going to get the 2/3 and the 2/15 are going to be repeated, right? Okay, in the third partial sum. And then what's the third term? Well, what do you get when you plug 3 into this formula for n? You get 4 times 3 squared, so that's 4 times 9 is 36, minus 1 is 35. So you have, as your third term, 2/35. And I'm not going to show the arithmetic here, but when you add 2/3 and 2/15 and 2/5 together, you end up with 6/7. Okay, so there's the third partial sum. So here, let's see, as our series looks like it's converging, we have 2/3 and 4/5 and 6/7, right? Okay, is that converging to something? Maybe 1 again? 6/7 is getting pretty close to 1. Maybe. I'm not sure, right? Okay, so how in the world are we going to analyze this series to see if it converges? Okay, so if you look at the kth partial sum in general, well, let's see, you have 2/3 plus, because that's S sub 1, right? You have, I'm sorry, that's the first term of the series, and then you have 2/15, and then you have 2/35, right? Plus, blah, 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 plus, what's the kth term of this series? It's 2/4 times k squared minus 1. Wow, I have no idea. Really don't know, right? I have no idea. Really have no idea how that's going to, what that's going to add up to, or, if we take the limit as k goes to infinity, don't really have a good idea of if there's going to be some limit there. So this one, when we look at it just in, just in a straightforward way, this series is hard to analyze, to think of it. Is it converging to something? Does it converge to 1? Or maybe it diverges? A little bit tough, right, to understand. And that's not unusual for a series, okay? They're not trivial to determine if a series converges or not, except in certain for certain particular types of series, and we're going to learn about those in a moment. But for this one, initially, it's hard to see, right? Okay, what's happening. All right, now, however, I'm going to show you that we have a little trick here that we can use to analyze this series. So we're kind of fortunate in this particular series. Okay, let me show you why. We can rewrite 2/4n squared minus 1. It's possible to rewrite that fraction. And because 4n squared minus 1 factors, so that factors as, this is difference of two squares, right? So that factors as the sum of the two square roots times the difference of the two square roots. Now, guess what I'm going to do? I'm going to take this fraction where the denominator is factored, and I'm going to break that up into partial fractions. So we're going to revisit some of our partial fraction skills from the previous chapter. And so you've already done this on the test, right? So you're good at taking a fraction and breaking it up into partial fractions. So I'm going to write this as this 2/2n plus 1 times 2n minus 1. I'm going to write that as the sum of 2 fractions. And I got to figure out what the numerator of this first fraction is and what the numerator of this second fraction is, right? But you know how to do that, right? Because if we add these two fractions back together, the common denominator, of course, is 2n plus 1 times 2n minus 1, right? So that means then that to add these fractions together, I would multiply the first fraction by 2n minus 1 over 2n minus 1. So I would have a times 2n minus 1, right, over 2n plus 1 times 2n minus 1. And then I would have b times 2n plus 1, right? So b times 2n plus 1 over 2n minus 1 times 2n plus 1, right? So you can add these two fractions together, but then what that tells me is that a times 2n minus 1 plus b times 2n plus 1, that has to be equal to 2. So I'm gonna figure out, right, how to make this, you know, what choices for a and b, right, will make that that numerator 2. So let's write that out, right? So I have 2 times 2n minus 1 plus b times 2n plus 1, right, is equal to 2. And now let's choose something for n, right? What do y'all want to try for n? 1/2, right? If n is equal to 1/2, then you'll have 2 times 1/2 minus 1 is 0, right? So this will 0 out. So you'll have b times 2 times 1/2 plus 1. That looks like 2, right, is equal to 2. So I think that means b is equal to 1, correct? And then what about if n is minus 1/2, right? What about if n is minus 1/2? Then when you plug a minus 1/2 into this term disappears, right? Because you have 2 times minus 1/2 is negative 1 plus 1, so that's 0. And then, but when you plug minus 1/2 in here for n, it looks like you get negative 2, right? 2 times minus 1/2 is negative 1 minus 1 is negative 2. So you get a times minus 2 is 2. With that, I think that means what? That a is equal to minus 1. Oh, nice. So so a is minus 1 and b is plus 1. So so really what this series is the sum from n equal 1 to infinity of, let's see, I'm going to write this fraction first because the b is positive, right? So I get 1 over 2n minus 1, and then minus 1 over, because a is minus 1, right, over 2n plus 1. So that gives me a little bit different perspective now on this series, right? Okay, because now I've made the terms look a little bit different, right? Let me see, minus 2n plus 1. Just want to make sure I did this, and then 2n plus 1. Yeah, okay. So all right, now let's, so now that we've got the terms rewritten in this form, instead of 2 over 4n squared minus 1, we have the terms written as 1 over 2n minus 1 minus 1 over 2n plus 1. Now let's rewrite the kth partial sum. So, so let's write in these terms. So what's the first term? When n is equal to 1, what do you get? When n is equal to 1, you get 1 over 1. 2 times 1 minus 1 is 1. So you get 1 over 1 minus 1 over 3, isn't it right? 2 times 1 plus 1 is 3. That is 2/3, right? So that is the right first term. And then plus, what's the second term now? So what do we get when n is 2? Well, you get 1 over 3 minus 1 over 5, right? So there's the second term. What's the third term? When n is equal to 3, we get 1 over 5 minus 1 over 7. Okay? Plus, well, plus a long way, right? What's the kth term going to be? So what happens when you plug k in for n? Well, you get 1 over 2k minus 1 minus 1 over 2k plus 1. Now, how is that helpful in analyzing the kth partial term, right? Well, look what happens when you add all these partial terms when you add all these terms together, right, to get the kth partial sum. Look, you have minus 1/3 and plus 1/3, so that disappears, and you get minus 1/5 and plus 1/5. And so this cancellation is going to keep on going, just like in our prior example. So S sub k nicely just works out to be the 1 is left, and here the minus 1 over 2k plus 1 is left. So that's really what S sub k actually adds up to. It's not as bad as it looks. It ends up being 1 minus 1 over 2k plus 1. So what is the limit now as k goes to infinity of the kth partial sum? Well, that's the limit as k goes to infinity of this quantity, right? 1 minus 1 over 2k plus 1. And, well, what happens as k goes to infinity here? This term goes to 0, right? As k gets large, 1 over 2k plus 1 is going to be getting close to 0, and all you're left with is 1. Yay! So this series does converge. It actually does converge, and it adds up in the end to just 1. So there's another series adding up to 1. Okay, so even though you're adding up infinitely many positive numbers, they don't add up to infinity for this series. They just add up to 1. So this series converges to 1. All right. Well, okay. I think you get the message, right? That sometimes series can be hard to analyze. Okay. Fortunately, there are certain types of series that occur quite frequently. And so they occur so frequently that they have been analyzed a lot, and so we understand a lot about these types of series. And so we don't have to do always this complex analysis to understand if the series is converging or if the series is diverging. An example of such a series that occurs frequently is what's known as a geometric series. Okay. And so, fortunately, geometric series have really easy properties to analyze. So, let me show you what a geometric series looks like. Okay, in a geometric series, terms always have the same form. It's going to be some coefficient times some base. These two numbers are fixed. Okay, so these two numbers are fixed, and then the base is raised to some power, and the power is the index of the series. Okay. By the way, this coefficient cannot be 0, and this base here of the power cannot be 0. But these are numbers, right? These are specific numbers. The only thing that's varying from term to term is this is the index, right? It's this exponent is the only thing that's changing. By the way, now, notice in this geometric series description, the index is starting at 0. That's important. Okay, so the index here starts at 0. You can have geometric series where the index does not start at 0, but in this description of geometric series, notice the index starts at 0. So if you write out the terms of a geometric series, you get a times r to the 0th power, a times r to the 1st power, a times r squared, a times r cubed, a times r to the 4th power, etc., etc., etc. Okay, so you're just getting adding up powers of this base, but you also have this possibly this coefficient thrown in, right? But you're always adding up powers of the same base. This base is called the ratio of the geometric series. All right. But you can also call it the base of the geometric series. But also known as the ratio of the geometric series. So so any series where the terms look like this, right? So you just have powers of the same base, right, are really what's forming your terms, and then times possibly some coefficient. That will be called a geometric series. And here's what we know about geometric series. All right, so they have a lot of they're easy to analyze. Okay, so if your base, if your ratio, and the ratio can be negative, but that's a little bit unusual. But if the ratio is negative, I'm sorry, if the absolute value of the ratio is 1 or higher, that means the geometric series diverges, okay? But if the absolute value of the ratio, the base, is less than 1, then the series will converge, okay? And here's what it converges to. It's easy to analyze what it converges to. It's just it's A over 1 minus R. It's got a very easy sum, A over 1 minus R. So remember, this formula is important. That's the geometric series sum formula, A over 1 minus R. But I do want to point out that in this formula, for your geometric series, the index begins at 0. So if the index if you have a geometric series where the index does not begin at 0, you have to think about that and adjust this formula, okay? So be careful of that, all right, when using this formula. This formula applies when the index starts at 0. All right, let's look at some series, okay? And if we're lucky, these will turn out to be geometric series, right? Okay, so let's look at this series. The sum from n equals 0 to infinity of 3 over 2 to the nth power. All right, so what do some of the terms of this series look like? So you get what? 3 over 2 to the 0th power. Let me write that in there. That's the first term. 3 over 2 to the 0th power. Right, see, when the index is 0, you get 2 to the 0th power, but that's just 1, correct? So you end up here just getting, for your first term, 3, because 2 to the 0th power is 1. What about the second term? Well, you get 3 over 2 to the first power. That's 3 halves. The third term, 3 over 2 squared. That's 3/4, right? The next term is 3 over 2 cubed, right? That's going to be 3/8, right? The next term is 3 over 2 to the 4th power. That's 3 over 16, etc., etc., etc. All right, so we want to know, like the same thing that we always want to know for series, does this series converge? And if it does converge, what is the sum? All right, let me show you now. This really is, although you probably can see this easily without me showing you, but this is really a geometric series, okay? Because you can rewrite 3 over 2 to the nth power in the following way. You can write this as 3 times 1/2, the fraction 1/2, raised to the nth power. And when you write it like this, then you can easily see that this is a geometric, whoops, I started my index at infinity. That's not going to help. All right, so when you write it, the terms in this form, you can easily see this is a geometric series, right? The coefficient here is 3, the a value is 3, and the ratio is 1/2, which is less than 1, so that tells me already that this series is going to converge, right? Okay, and since it converges, what sum does it converge to? Well, that's where our geometric sum series sum formula can help us, right? So it's going to be A 3 over 1 minus 1/2. Just that easy, right? So it's 3 over 1/2, which is 6. So the terms of this series add up to 6, right? So see, it's really helpful to recognize if you have a geometric series because they're very easy to analyze. Fortunately, geometric series occur quite frequently, all right, in practice. So here's another very clear geometric series, right? You have the sum here from n equals 0 to infinity of there's a base, right? Raised to a power, right? Okay, so here the coefficient is just 1. You can think of the terms here as having a 1 multiplied in. So the a value is 1, and the ratio here is 3/2, right? Because that's the base that you're raising to a power in each one of your terms of the series. But this is bigger than 1. Actually, it only has to be bigger than or equal to 1. If it were equal to 1, you would get the same result, which is this series does not sum up to a finite value. This series diverges. So these powers are going to not add up to, they're going to add up to infinity, right? This series diverges. Just that easy to see. Okay. I'm going to skip these 2 examples, and I want to show you now. So there's just 2 examples of geometric series, but geometric series are easy to understand, so I don't think they'll be that challenging for you on the homework. Now, I want to show you here, we're going to learn several tests that we're going to use to understand if a series converges or if a series diverges. But I want to point out that even when you decide that a series converges, so even if you know a series adds up to a finite amount, it can often be difficult to determine what the sum is, okay? So determining if a series converges and determining what the sum of the series is are 2 separate problems, and the sum problem is often much harder than the convergence problem, okay? But we have to start somewhere. So I'm going to show you just some tests here, and here's the first one that you can use to decide if a series converges or if a series diverges. All right, and again, there are going to be quite a few of these tests that we're going to learn. All right, so here's the first one, and this is called the divergence test, or the nth term divergence test, I should say. And you have to be careful to apply this test properly, because it doesn't always say everything that you hoped it would say. But here's what the test says. So this is, again, the nth term divergence test. Okay, so this says, look, if you're looking at a series, right? Okay, it doesn't matter, by the way, if the the index begins at 1 or if the index begins at 0. Actually, it doesn't really matter where the index starts at there in this theorem. They have them starting at 1, but that's not really important to applying this theorem. What this theorem says is, if your terms do not go to 0, all right, so as your index gets larger and larger, if your terms are not getting smaller and smaller, if the terms are not going to 0, then the series has to diverge. That makes sense, right? If you're adding infinitely many terms together and the terms are not getting smaller and smaller, if the terms are not going to 0, then that means there's no way those terms can add up to a finite quantity, right? The sum of that series has got to be infinite, all right? So pay attention to that, right? So if you're looking at a series and you notice that the terms of the series are not getting closer and closer to 0, right, as n gets large, as the index gets large, that means you know automatically that the series is going to diverge. Now, I have to caution you that the converse of this theorem is not true. Just because the terms are getting close to 0 does not mean that the series converges. Okay, so you understand what I just said? You can have series where the terms are getting close to 0. As the index gets large, the terms are getting close to 0, but the series still diverges. Okay, but if the terms are not getting close to 0, then definitely the series diverges, right? So that's all this theorem says. Okay, so be careful about applying this theorem properly. All right, so let's actually apply the theorem. So look at this. Series. So here, notice you're adding together powers of 2. Okay, you're adding together powers of 2. So look at the terms of this series. What's a sub 0? What's the first term when n is equal to 0? Well, you have 2 to the 0th power, which is 1, right? What's the second term? Well, you have 2 to the first power, which is 2, right? What's the next term? That's 2 squared, which is 4, right? So on and so forth, right? What's the kth term here? That's 2 to the kth power, right? Whatever that is. So so does this series converge or does it diverge? Okay, you automatically know this series is going to diverge. Why? Because look at the terms of the series. They're not getting smaller and smaller, right? In fact, the terms of the series, right, the things that you're adding together in the series, they're getting larger and larger as your index gets larger, right? They're not getting closer to 0. In fact, they're getting further away from 0. So that means definitely that the series diverges, right? Okay, the terms have to be getting close to 0 as your index gets larger. Otherwise, the series cannot converge. Let's look at, the B is a little bit more complicated, so let's look at our last example next, okay? So let's see here, all right? So what's happening to our terms here, okay? So what's a sub 1? Well, that's 1 over 1, which is 1, right? What's a sub 2? That's 1 over 2, which is, well, 1 over 2, right? That's 1 half. What's a sub 3? That's going to be 1/3, right? What's a sub 4? That's going to be 1/4, etc., right? What's the kth term? A sub k would be 1 over k. So you're looking at this series and you're thinking, oh, well, that's great, right? My terms, right, that I'm adding together, they are getting closer and closer to 0, right? They're getting smaller and smaller. So you have 1 plus 1 half plus 1/3 plus 1/4, etc., up to plus 1 over k. So my terms are getting smaller, getting closer to 0, right? So that means the series must converge. No, that does not mean the series converges, okay? Right? All we know is, so far, all we know is if the terms are not getting smaller, not getting closer to 0, then the series must diverge. But it's not the case that if the terms are getting smaller, that the series always converges. Sometimes it will converge and sometimes it won't. And actually, this series is going to diverge. All right, even though the terms are getting close to 0, right, as the index gets larger, the terms are getting close to 0, this series still diverges. This is a very famous series. This is called the harmonic series, and so so I want you to pay careful attention to this series. It diverges, all right, even though the terms are getting close to 0, the series still diverges. Again, because the theorem says, does not say if the limit is of your terms is 0, then the series converges. What the theorem says is, oh, if the limit of the terms is not 0, then definitely the series diverges, right? But the converse is not the case, all right? So keep this series in mind, this so-called harmonic series. This is a very useful series to remember, that this series actually diverges. It does not converge. 1 plus 1 half plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7, etc., out to infinity. That does not add up to a finite number. That actually adds up to infinity. All right. All right. So let's look at this more complicated example, and this will be our last example for these notes. All right. So this was a little bit more complicated because it has some new notation in it that we haven't looked at before in the class. So I've got to explain this notation. You may be familiar with it. It's this exclamation point notation that's called factorial, and that represents a particular arithmetic operation. And it's very easy to understand that arithmetic operation, but I'll explain what it is. All right, so here are the terms of our series. we're going from n equals 0 to infinity here, is n factorial. This is how you read this, factorial. That exclamation point you read is factorial. Over 2 times n factorial plus 1. So again, you read that exclamation point, not as exclamation point, but you read that as factorial. And I explain what that factorial means here in just a second. Okay, so well, let's write out some terms of this series. Okay, so the first term, when the index is 0, that will be 0 factorial over 2 times 0 factorial plus 1. And then second term is going to be 1 factorial plus 2 over 2 times 1 factorial plus 1, right? Third term is 2 factorial over 2 times 2 factorial plus 1. Next term is 3 factorial over 2 times 3 factorial plus 1, etc., 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 right? Okay, because we've got infinitely many terms in this series. Now, we actually want to compute what these fractions are, but to do that, I've got to explain to you what this factorial notation actually means. Okay. All right. So here's what it means. In general, when you take it has to be a positive, well, a non-negative integer, and you put the exclamation point on it. What that means is you're going to take the product of that number and then all integers smaller than that down to 1. So, for instance, 5 factorial, 5 with an exclamation point, that means 5 times 4 times 3 times 2 times 1, right? Get the picture, right? Factorial is a way of summarizing a product. So 5 factorial, 5 times 4 times 3 times 2 times 1, which turns out to be 120. 3 factorial is going to be 3 times 2 times 1. All right, so you just take with this number and then just multiply all the integers less than that down to 1. So 3 factorial is 6. 2 factorial, easy, that's 2 times 1, right, which is 2. 1 factorial is just going to be plain old 1. Now, that definition that I just gave you doesn't really apply to 0, but we can compute 0 factorial. By definition, just by definition, 0 factorial is said to be 1. Okay, so keep that in mind. So in general, n factorial would be n times n minus 1 times n minus 2, etc., times n minus 3, all the way down to last factor is 1. And this these sorts of products occur frequently in mathematics, where you take, a number and then times 1 less, times 2 less, times 3 less, times 4 less, etc., down to 1. That product occurs quite frequently. That type of product occurs quite frequently in mathematics, and it's kind of clumsy to write all that out, right? So that's why the factorial notation was developed. All right, so let's actually fill in some of these factorial values now and see what these fractions actually are. So remember, 0 factorial is 1, right? So you have 1 over 2 times 0 factorial is 1. So you have 2 times 1 plus 2, that's 3. And then let's see what's happening here. 1 factorial is 1. So you have 1 over 2 times 1 factorial. 2 times 1 plus 1 is, that's 3 again. Okay, so you have 1/3 again. And then let's see what's happening here. 2 factorial is 2, right? 2 factorial is 2 times 1, which is 2, over 2 times 2 factorial plus 1. That looks like that's going to be 5, right? And 3 factorial we said was 6. So you would have 6 over 2 times 6 plus 1. That looks like it's going to be 13, okay? So there's the first few terms of our big series there. 1/3, 1/3 is the first term, 1/3 is the next term, 2/5, 6/13. And we're going to add all those fractions together right out to infinity. And we're wondering, does that converge or does that diverge? Ooh, really hard to tell, right? Because it's really hard to tell what's happening to these terms. But I'm going to show you a little trick here that you can use to analyze this particular series. I'm going to take everything in this fraction here, n factorial over 2 times n factorial plus 1, and I'm going to divide everything by n factorial. So I'm going to divide this n factorial by n factorial, and I'm going to divide this 2n factorial by n factorial, and then I'm going to divide the 1 by n factorial. So that doesn't change the fraction when I divide everything in the top and bottom by n factorial, but there's a reason that I did that, as you'll see here, because n factorial over n factorial is 1, and then this reduces to 2. So you have 1 over 2 plus 1 over n factorial. So that's another way of writing the terms of your series. Now, the reason that I divided everything by n factorial is look what's happening to these terms as n gets larger. So as n starts approaching infinity, look what's happening to these terms. Well, as n gets really large, notice 1 over n factorial is going to be getting small, right? Because n factorial is also going to be getting large, right? As n gets large. And so this fraction is really going to 0 as n goes to infinity. So what your terms are really getting close to is 1/2, right? As your index gets larger, your terms are really getting close to just 1 over 2, which is 1/2. But guess what that means? That means your series diverges, right? Because remember, for the series to converge, your terms have to get close to 0 as your index gets large. But in this series, as the index gets large, the terms are just getting close to 1/2. Look, 1/3, 1/3, 2/5, 6/13. If we continue writing out these terms, we're going to get fractions that are closer and closer to 1/2. But 1/2 is not 0. So our terms are not going to 0. They're going to 1/2. But for a series to converge, the terms have to be getting close to 0 as the index gets large. So this series is going to not sum up to a finite number, right? It's going to diverge. It's going to sum up to infinity. Okay, well, there's a quick introduction there to series, and so we're going to take up again in our next notes, right? Again, some more tests that we can use to determine if a series converges or if a series diverges, right? But remember, for geometric series, right, you really don't have to conduct any of these tests, right? If you recognize that a series is a geometric series, right, then you automatically know whether it converges or not, correct, right? And you know also, if it does converge, what the sum is, right? So keep that in mind when you're working on your series homework. Okay, well, so we're done for our lecture for today, Wednesday, April 15th, right? Okay, and so I'm going to see you again on Monday, what is that, April 20th? That will be our last full week of class, because our last class day, again, as I said earlier, is April 27th, right? And that will be the day of our third test. So be sure you're keeping up with your homework, right? Okay, that's really important, especially since we're getting here close to the end of the semester. So I'll see you guys next Monday. Stay safe as always, right? Bye.